In this lecture, we will solve a wide variety of heat conduction problems in rectangular, cylindrical, and spherical geometries. We will limit ourselves to problems that result in ordinary differential equations rather than partial differential equations, just to make it easier. And some of you probably haven't had uh, a course in partial differential equations, so this will make it a little bit easier and something you should have seen in when you took ordinary differential equations. Um, we also assume that we have a constant thermal conductivity, so the K value is going to be constant. That will make it easier as well. First off, let's look at example 210. This is a rectangular coordinate system kind of problem. So we have heat conduction at a plane wall. So we have a large plane wall of thickness 0.2 meters. It has thermal conductivity of 1.2 watts per meter Kelvin and a surface area of 15 square meters. The two sides of the wall are maintained at constant temperatures of 120 and 50 degrees C respectively. Determine the variation of temperature within the wall and the value of temperature at x equals 0.1 meters and the rate of heat conduction through the wall under steady conditions. So here we have a problem where we have constant boundary conditions on the outside and inside wall. We want to determine the temperature and the rate of heat transfer. So our assumptions here are that heat conduction is steady, it's one-dimensional, the thermal conductivity is constant, and there's no heat generation within inside the wall. So here's our problem graphically. We have a plane wall, we have two temperatures on each side, and the wall has a certain thickness L. So this is essentially a one-dimensional problem, and it's a steady state problem. So we can take a look at our general rectangular coordinate heat conduction problem. There's no function. It's not a function of y or z, so those terms can go away. There's no heat generation inside the wall, so that term can go away. And the temperature is not a function of time. It's constant. So that term can go away. So this all simplifies down into a very simple ordinary differential equation. The double derivative of temperature with respect to x is equal to 0. And then we apply the boundary conditions that the temperature at 0, when x is 0, is 120 degrees C. The temperature when x is equal to L is 50 degrees C. So now to solve this, we simply need to take two integrations. So the first integration, you get that dt dx is equal to some unknown constant. Let's call it C1. If you take another integration, you get the temperature is equal to C1x plus C2. So this is what's known as the general solution to the differential equation, because we have two unknown constants, C1 and C2. How do we determine those constants? Well, we have to apply our boundary conditions. We've determined that the general solution is given by the following equation. So now, to determine the unknown constants C1 and C2, we simply apply our boundary conditions, shown here. So if we plug when x is equal to 0 here, this term goes away and we're equal with C2. So C2 has to be equal to 120 degrees C. We plug in, use the second boundary condition, the temperature at L is equal to C1 times L plus C2. So we can solve this. This has to be equal to T2, so we can solve this for C1. So C1 is equal to T2 minus T1 over L. So we know what T2 is. It's 50. We know what T1 is, 120, and we know what L is. So we can solve this and plug what C1 and C2 are back in the original equation here, and we end up with our simple equation. So this is simply just a straight line, y equals mx plus b, if you will. So in this particular part, we were asked to find the variation of temperature within the wall when the value of temperature is at x is equal to 0.1 meters. So here's our equation we derived. We can plug in 0.1 meters. We know what T1 and T2 are, and we know what L is. It's 0.2. So we can plug this in, and we determine that it's 85 degrees C. We're also asked to find the rate of heat conduction through the wall under steady state conditions. So here we have the equation. Heat conduction rate is minus Ka dt dx. So we're going to approximate this, but you know, we don't. We could take a derivative here and plug in, but this is approximately delta t over delta x. So K is given, the area of the wall is given, because we know the dimensions. Delta T is 50 minus 120 degrees C. Delta X is 0.2, so we can calculate that to be 6,300 watts. Example 215 walks through exactly the same kind of thing, except it uses cylindrical coordinates. It gives us the temperature differences on the inside and outside wall. It gives us the pipe length, L. It gives us R1 and R2, the two different radii of the cylinder. So here we just want to obtain the general relation for the temperature distribution inside the pipe and determine the rate of heat loss from steam through the pipe. So again, we're going to assume the standard assumptions. Heat transfer is steady. There's no change with time. It's one-dimensional. It's only a function of R. Thermal conductivity is constant, and there's no heat generation within inside the wall. So here, in general, the heat conduction equation in cylindrical coordinates is given by the following. But of course, this term is zero because it's steady state. The E.gen term is zero because it's not. We're not generating any heat within the wall itself. There's only heat passing through it. It's not a function of phi and z, so these terms go away. And since it's only a function R, we can sort of factor the k out and divide through by it. So this most general equation reduces down to something a lot simpler. And we're given the boundary conditions at the temperature on the inside and outside walls. So again, this problem is pretty simple. We start with our equation we just developed. We integrate once. So you integrate on this side, you get rid of the d over dr. You integrate on this side, you get a constant. Then we can integrate again on both sides. So to do that, you can divide both sides by r. You get dt over dr is c1 over r. Integrate both sides. So over here you get a t as a function of r. Over here you get a natural log, and you got another arbitrary constant. So this is our most general solution. We have two unknown constants, and we're going to use our boundary conditions to determine what they are. So here's our equation we just developed. You go through exactly the same kind of process as we did for the rectangular one. You take this equation, you plug in what R1 is. You take this equation, you plug in what R2 is. So you can determine what the unknown constants are, C1 and C2. So we can substitute back in the equation here, and we can find for C1 and C2, we can find our solution looks like the following. So we want to find the rate of heat loss from the steam. That's simply the total rate of heat conduction through the pipe. So Q dot is minus Ka dt over dr. So A, it's a cylinder, so it's 2 pi RL for A. So here I pull the 1 over R by itself, and so you get a delta T over delta R. This is C1. This value here is C1. From the previous, if you go back a couple slides, you just plug in what C1 is here, and it's delta T of the log of the ratio of the radii. So you can cancel out the R here and the R there, and you end up with the heat loss equation for the cylinder. If you plug in the conditions for K and for L, delta T, and the log of the ratio, the radii, you get it's 786 kilowatts is the rate of heat loss. Example 216 is through a sphere, similar kind of problem. It gives us the radii of the sphere, inside and outside radii. It gives us K. It gives us the temperatures on the boundary again, inside boundary and outside boundary. Those are two boundary conditions. Same assumptions, so I'm not going to go through that again. Turns into a one-dimensional heat conduction problem again. So, if you take back in lecture, I guess it was lecture 3, where we talked about the most general types of rectangular, cylindrical, and spherical equations. The spherical one reduces down to this one. I didn't put the whole equation up here because it's exactly the same as the previous two analogies. It's one-dimensional. There's no Egen term. It's only a function of r. Makes it pretty simple. Here's our boundary conditions. So again, exactly the same kind of deal. Integrate once, integrate twice, determine what C1s and C2 are by plugging them in. So here's the integration twice, plug in the boundary conditions, solve for C1 and C2, then plug them back in the initial equation. Gets kind of old after a little bit. Same. So if you plug back in, you can determine the equation. So R1, R2, all the stuff we know, that's all constants. T1 and T2. So given an R, we can calculate what the temperature is. So the heat loss is minus Ka dt dr. So surface area of a sphere, 4 pi r squared. dt over dr, that's turns out to be C1 over r squared. So C1, you can plug what C1 is in there. The r squareds cancel, and you end up with this equation here. So specifically, we can calculate what the rate of heat conduction through the wall is, because we know K, we know the dimensions of the sphere, we know the temperature difference, we know what R1 and R2 are. Interestingly, so this is the same for for at every point. However, if you divide Q1 dot by the area, which is the heat flux, you see it's actually different, right? So at the inside wall here, it's this amount. On the outside wall, it's that amount. So while Q is the same, it's not going to change from inside to outside. Small q does.